as NASA's space portals blink out and terrestrial scopes get dazzled by solar glare. The third verified interstellar visitor, dubbed 3I/Atlas, hurtles beyond Mars at a distance of 30 million kilometers. It's the pinnacle of astronomical paradox. Precisely when this odd, verdant luminous wanderer reaches its nearest point, U.S. scientific channels abruptly go silent. Solely the Martian satellites from European, Chinese, and Emirati programs can capitalize on the opportunity, snapping the clearest snapshots and gathering vital info that ground-based views on Earth miss entirely, all before 3I/Atlas slips into obscurity for good. Yet, as premier observatories worldwide scramble to redirect amid the urgency, what secrets might the Mars Vantage reveal about this entity that shatters conventional comet norms? Time for this extraterrestrial brush is already running short. Come October 3, 2025, the orbital alignment seals Earth off from the spectacle, with 3I/Atlas gliding by Mars at a mere 0.2 astronomical units, roughly 30 million kilometers. The Sun positions itself squarely in our line of sight to the comet. From our planet's viewpoint, the elongation, the angular gap in the sky between the Sun and 3I/Atlas, narrows to less than 10 degrees. That's a firm barrier for Earth telescopes. The majority of facilities won't endanger their lenses or detectors by pointing at objects closer than 15 degrees to the Sun. Heading into early October, the comet's spot plunges deep into that risky territory, not merely for an evening or so, but across almost 6 weeks, from the end of September into the start of November. In contrast, Mars lingers in its path, shifted by over 40 degrees from the direct line. The angle formed by the Sun, 3I/Atlas, and Mars on October 3 stands wide open, frequently exceeding 50 degrees. Consequently, probes orbiting and rovers roaming the rusty world enjoy a pristine, glare-free perspective, even as every terrestrial observer gets overwhelmed by sunlight. The figures paint a vivid picture. Right at peak proximity, our planet's gaze is obstructed, leaving Mars with prime viewing access. Whatever shift, eruption, or irregularity emerges in 3I/Atlas's activity over this interval will register initially, or exclusively, via the devices encircling or traversing the crimson sphere. During this fleeting period, the red planet assumes the role of the solar system's sole sentinel. Any delay translates to an irreversible void in the archives. The time frame for observations from Mars isn't counted in weeks or days anymore. It's mere orbits, a narrow opportunity before the comet accelerates onward and alignments shift once more. Typically methodical, with timelines spanning months in advance, mission coordinators must now adapt on the fly. Routine procedures yield to urgent redirects. Tools meant for probing Martian craters or sifting the sparse atmosphere get repurposed toward the void. Communication streams tuned for steady, incremental research suddenly manage floods of unprocessed signals and preliminary visuals, racing to document any surge or oddity before it dissipates. The strain never lets up. With each overhead trajectory or data transmission, there might lie the final shot at spotting a fresh detail or unexpected burst. No room exists for red tape or hesitation. Success hinges entirely on the agility and decisiveness of the crews steering those remote probes. The red planet falls under surveillance from various orbiters, each tailored to a distinct range of the spectrum and overseen by separate control groups. Europe's space agencies Mars Express and the ExoMars Trace Gas Orbiter have locked in frequent imaging sessions for the October 3 week. Mars Express deploys its advanced stereo imager and Omega analyzer to produce detailed color range photos and probe elemental traces across visible and infrared bands. The Trace Gas Orbiter's Nomad and ACS instruments break down the comet's emissions into myriad spectral lines, hunting for exotic vapors and compound signatures. These craft can swing from Mars to follow the intruder, though each adjustment weighs against heat limits and operational risks. Preliminary results could surface in days, yet comprehensive datasets for the public often emerge months down the line, post-processing and checks. The United Arab Emirates HOPE probe offers a fresh angle. Its XS imager and EMIR's ultraviolet tool, normally dedicated to air studies, can shift to surveil luminous targets against the Martian backdrop. Hope's broad circling path and adaptable orientation equip it ideally for expansive views and UV readings, particularly should the operators greenlight a swift action plan. In previous comet flybys and solar disruptions, Hope has shared refined outputs in under a week if the findings demanded it. China's Tianwen-1, outfitted with fine and coarse-grained cameras plus a mineral mapping spectrometer, stands ready to deliver background shots and near-IR profiles upon redirection. While formal endorsement for a 3I/Atlas effort remains awaited, Tianwen-1's outputs usually reach wider audiences via organized drops or research publications, potentially weeks or months post-acquisition. NASA's Mars Reconnaissance Orbiter, featuring the HiRISE Imager and XRISM spectrometer, boasts prior experience with comet and asteroid pursuits. Off-nominal aiming relies on cleared protocols and vehicle well-being. The ongoing U.S. federal shutdown further hinders timely sharing of fresh internal groups. Keep watching the spacecraft's condition and ensuring planetary safety, even if the MRO picks up the data. Elsewhere in the solar system, the European Space Agency's JUICE probe plans to catch glimpses of Comet 3I/Atlas during its journey outward in November's early days. The viewing conditions aren't ideal, and its tools, JANUS, MAZE, and UVS, are optimized for far-off dim objects. Whatever info JUICE records will endure a lengthy data transmission backlog, with no public sharing anticipated before early 2026. Still, even a handful of spectral readings or snapshots might aid in following the comet's behavior as it swings around the Sun. This array of efforts creates a multi-tiered strategy, where every mission adds its own perspective and wavelength coverage. Certain outcomes will emerge quickly, in mere days, while others require extended checks over months. The phased data drops and collaboration across organizations mean the tale of 3I/Atlas will reveal itself gradually. Every batch of information serves as a possible key insight. 9 minutes. That's how long the Perseverance rover fixed its lens on the Martian heavens on October 2nd. Every shot from the right Mastcam Z includes an exact UTC time mark plus details like shutter speed, color filter, and lens angle. The series was meant for atmospheric scans, yet something unusual showed up this route. Aligned streaks through the star paths, not matching any satellite orbits or the leisurely shift of planets. Calibration comes first. Unprocessed photos go through a processing chain, evened out for lighting, cleared of dark noise, fixed for faulty spots. Investigators must chase down and dismiss every flaw, from radiation hits to lens echoes. The Mastcam Z team's processing routine is routine for them. They assess the background glow, verify light measurements, and sync the shots. That's when the mark becomes clear, a dim, swift streak that persists across frames. Next up is positioning analysis. Experts load the SPICE data files, NASA's system for converting rover aim to celestial positions. They layer the comet's forecasted track from JPL's orbital predictions onto the photo series. The streak's direction and pace clock in at about 400 arcseconds, lining up with 3I/Atlas's expected movement from Jezero crater at that moment. The bearing fits, the velocity matches, but alignment isn't proof. They have to rule out fakes. Radiation strikes typically scar just one pixel sharply, not drag on smoothly over several images. Lens flares or echoes shift with motion, but this line stays put. Software runs averaging filters and outlier removal to filter fleeting noise. Each possibility gets flux readings and scans for brightness changes that might signal equipment issues or atmospheric particles. Then photometry steps in. The line is subtle yet steady. Its intensity, gauged end to end, fits what a hazy, quick coma would yield from Mars range. The brightness profile remains even, no flares, no dips. Team members match it against simulations of comet flares and sun glints. All seems in order. The ultimate check is the alignment. They graph the streak's spot versus the orbital forecast for 3I/Atlas. The deviations between predicted and actual spots stay under a few arcseconds, comfortably within tolerance. From so far away, the case builds, though formal approval remains pending. The U.S. government closure has quieted JPL's device experts. their evaluation is paused. Outside researchers, such as Simeon Schmosheim, have shared their results, but the full validation process hinges on NASA's go-ahead. The implications are huge. Should this trace hold true, it'd mark the initial ground-based sighting of an interstellar visitor from an alien world, yet research insists on thoroughness. Every phase, processing, positioning, light analysis, fake detection, needs to hold up under review until the MASTCAMZ specialists at Arizona State and JPL chime in. The field waits tensely. That trace lingers in 9 minutes of Martian night sky. Its status as a breakthrough find or a lesson in caution rests on future developments. Back on September 25th, one backyard telescope in Namibia provided the final sharp image of 3I/Atlas before Earth's view was blocked by the sun. Snapped from southern hemispheres mere hours prior to the comet entering solar glare, the photo showed a green haze spanning almost 700,000 kilometers, roughly double the Earth-Moon separation. The nucleus shown emerald, a shade rare among inner solar system icy bodies. Sun rays passing through vapors rich in C2 molecules and similar compounds dispersed to create a striking, eerie tint. Yet the form was even odder. Rather than the classic backward dust stream of standard comets, 3I/Atlas sported a forward-pointing tail, a broad fan of stuff aimed at the sun. This odd trait, formed by hefty, sluggish particles and the comet's unusual outsider trajectory, made it resemble a floating wedge more than a typical streaker. Faint streaks and subtler arcs emanated from the core, indicating successive outbursts or shells instead of a continuous outflow from stellar winds. Additional image sequences captured on September 27th and October 2nd, despite increased noise and interference from brightness, verified this unusual configuration. The object surrounding haze maintained its distinct contours, even as brightness diminished, defying the typical blurring and stretching associated with dust-dominated tails. Successive observations only strengthened the impression that this wasn't a conventional icy wanderer, but an entity governed by unconventional mechanisms, an outsider adhering to its own principles. These final glimpses, gathered just prior to Earth's temporary observational blackout, now established the foundation for all forthcoming views from Mars. The metrics for 3I/Atlas fail to align with established comet behaviors. Consider its pace first. Typical long-period icy bodies enter the inner solar system sluggishly, at speeds of 20 to 30 kilometers per second. This one shows no such deceleration. It hurtles by Mars at close to 60 kilometers per second, and projections indicate a peak of 68 kilometers per second as it reaches perihelion late in October. Such velocity outpaces even the swiftest known solar system comets. The path itself proves equally odd. Rather than diving in at a sharp, unpredictable incline, 3I/Atlas closely follows the ecliptic plane. Its orbital tilt deviates by merely a handful of degrees from the planetary alignment. For an authentic extrasolar interloper, this alignment is exceptionally uncommon. Interstellar arrivals are generally anticipated from elevated trajectories, not gliding indiscreetly along the system's primary orbital route. Dimensions present another enigma. Initial luminosity assessments, combined with haze simulations, suggest a central body exceeding 5 kilometers in diameter, perhaps larger. This ranks it among the biggest extrasolar objects detected, comparable to 2I/Borisov and surpassing Oumuamua in scale. Yet the haze formation raises greater bafflement. Lacking the traditional elongated dust trail pointing anti-sunward, it features an expansive, stratified sheath. Light polarization analysis suggests nested rings or bows. Each layer scatters sunlight with nuanced variations. Absent any extended fibrous appendage, this vast, organized nebula challenges fundamental comet dynamics. Both polarimetry and visual captures underscore the irregularity. The haze's verdant hue, caused by C2 molecules, is prominent, as is its endurance. Even under intense solar radiation and proximity to a coronal mass ejection, the shape remains largely unaltered. Velocity figures, orbital slant, dimensions, and sheath architecture combine to form a profile alien to comet norms. For orbital simulators, every measurement poses a novel hurdle. with standard methodologies yielding scant insights. On September 25th, 3i/Atlas faced an alternative trial, a coronal mass ejection launched directly from the Sun. Space weather experts monitored the CME's progress across the void, forecasting a wave of energized particles and magnetic disruptions. For ordinary comets, such as solar outbursts spells disorder. Incoming high-energy plasma often erodes ions from the sheath, sparks intense vapor release, and reshapes appendages swiftly, sometimes within hours. Experts at ion facilities and sun-watching stations anticipated a classic outcome, perhaps a collision wave, a surge of charged vapors, or a noticeable distortion in the object's aura. Yet the event unfolded subdued as the CME overtook 3i/Atlas. Earth and Mars-based scopes documented the consequences. Far from a spectacular ignition or reconfigured haze, the structure exhibited scant alteration. The emerald glow remained sharp. The countertail preserved its tapered profile, while peripheral layers displayed no evidence of abrupt swelling or breakup. Changes in form were negligible. No evident charged tail emerged, no sudden glow intensified, and the haze's banded rings showed no undulations. To plasma specialists, this outcome posed a riddle. They had foreseen heightened ionization, an inflated sheath, or traces of magnetic chaos etched in the emitted light. The lack of pronounced response sparks inquiries into the body's makeup and inner makeup. Does the haze possess exceptional toughness? Or does its molecular makeup repel solar disturbances? Devoid of a prominent ion trail or sudden spectral flares, conventional analysis tools falter. Investigators now turn to Mars satellite plasma detectors and rapid spectral scans for hints, anticipating that amid the unprocessed data streams, signs of that solar eruption lurk, ready for discovery. The trajectory of 3i/Atlas unequivocally reveals its provenance. It slices through the solar domain along a hyperbolic arc, untethered and one-way, bearing the clear signature of extrastellar passage. This trait alone groups it with just two prior intruders, 1i/Oumuamua and 2i/Borisov. However, confirming its roots is merely the entry point. The true difficulty lies in nomenclature and the reliability of classifications. Certain scientists opt for the term interstellar comet, invoking the verdant haze, the gas emissions, the tiered sheath. Others demur, highlighting the absent dust trail, the backward-pointing tail, the persistently consistent framework, and the elevated, nearly automated pace. The discussion goes beyond mere wording. It centers on proof and the threshold for bold assertions. Scientific progress relies on doubt, on questioning not only what aligns, but what withstands subsequent evidence. The experiences from 1i/Oumuamua are still vivid. Theories proliferated. Conjecture outpaced reality. Yet only solid figures persisted. For 3i/Atlas, each irregularity, each unusual hue, each envelope, each steady nucleus demands scrutiny, not exaggeration. The issue isn't if it might be artificial, but if any observation demands such a conclusion. Absent that, the sole indisputable fact is its origin from beyond our solar system. All other aspects stay as theories, pending the upcoming spectral analysis, the next photograph, the next revelation. For observers tracking the 3i/Atlas saga as it develops, essential resources include public datasets and crowdsourced evaluations. Begin with the project data repositories. ESA's Planetary Research Repository, the Emirates Mars UV Information Hub, and the UAE HOPE Probe's freely available platform. These serve as primary sources for preliminary visuals, wavelength readings, and occurrence notifications. The ExoMars Trace Gas Orbiter and Mars Express typically share their preliminary outcomes in days or weeks, often in Level 1 or Level 2 calibrated formats, occasionally with preview-level JPEG images. For the quickest insights, unofficial discussion groups such as the Minor Planet email list and the Comet Monitoring Archive follow unprocessed submissions and highlight possible oddities right away. Confirmation occurs in stages. Upon reports of a fresh streak or flare-up, compare the sighting against orbital forecasts from JPL Horizons or IMCC. Seek corroborating signals in intersecting datasets from Mars satellites, Earth telescopes run by enthusiasts, or even sun-watching facilities. Volunteer experts frequently release comparative image overlays, light measurements, and trajectory models in mere hours, particularly if formal outlets are delayed by closures or information restrictions. To track the shape's changes as 3I/Atlas nears its closest solar approach, observe the progression of the envelope's form in successive updates. Be alert for abrupt shifts, layers, curves, or backward tail intensification that might indicate renewed outbursts. The deepest insights will emerge from aligning unprocessed, time-stamped photos from various probes and spectral bands, rather than relying on refined announcements. At this juncture, openness and backups are crucial. Diverse sensors, separate groups, and prompt sharing of unedited information are vital for spotting details that could otherwise go unnoticed. On October 3, 2025, 3I/Atlas came within just 30 million kilometers of Mars, as ground telescopes on Earth were obscured by solar alignment and AUS federal closure. Orbiters around Mars from ESA, the UAE, China, and NASA provided the only views, gathering details inaccessible from our planet. Initial snapshots verified a greenish envelope spanning over 700,000 kilometers and a swift velocity approaching 60 kilometers per second. However, critical uncertainties linger. The actual makeup of 3I/Atlas, the cause of its stratified envelope, and the lack of a typical dust trail. Even after a near miss with a solar coronal mass ejection, anticipated charged particle effects proved slight. As global researchers analyze their observations and gear up for phase data disclosures, many elements await clarification. The verified extraterrestrial source of 3I/Atlas stands firm, yet its characteristics test existing comet theories. Until fresh information emerges, the narrative of this interloper stays incomplete, underscoring that despite worldwide resources, certain celestial enigmas persist. Music.